In this video, we'll be looking at the basics of exponential functions. What are they, what their graphs look like, and what their equations look like. So the basic exponential equation is going to look like f of x is equal b to the power of x. We would denote b as the base, and it also always has to be a positive constant. The x value is again still your variable, so the important note in terms of an exponential function is that the variable is specifically in the exponent. If the variable is not in the exponent, then this is not actually an exponential function. So we can look at some examples of these. F of x might be equal to 2 to the power of x. Again, the base is then 2, where the variable exponent is x. Then you might have, say, 10 to the power of x. Now, these two specific bases have importance in terms of the way we look at them. This one here is actually called the common base. There's another base. I'm going to go ahead and write that down. That's e to the x. This is called the natural base, such that e is a number very much that like pi. It's e is equal to approximately 2.71819 ... Continues on forever, never stops. Again, this natural base is extremely important in most mathematics. And does show up quite a bit later on. Some other functions that you might add to the complications of what we're looking at is, say, 3 to the power of x plus 1, or maybe even, say, 1/2 to the power of x minus 1. And these are all different types of exponential functions. Again, notice the variable is in the exponent. There can be other things in the exponents. You can, again, make some of these more complicated by adding extra details to it. For instance, the plus 7 is at the same level as the base, so it's not in the exponent. And that's basically, again, what the types of potential exponential functions can look like. The next thing we do is how do we evaluate these things? So if I want you to evaluate an exponential function, you'd be looking, say, finding f of 3, given specifically that f of x is equal to, let's say, 7 to the x minus 300. Then we're going to just simply go ahead and replace the x. Again, all the x's, just like we would with algebra. F of 3 is equal to 7 to the power of 3 minus 300. And 7 to the power of 3 should be something along the lines of 343. So 343 minus 300 ends up giving you simply 43. So again, to evaluate exponential functions, you do nothing different than would you evaluate a regular function. Now let's talk about the graph in terms of the way they appear. So in terms of a graph and exponential function, if we're looking at the basics of f of x is equal to 3 to the x, now you might want to first start off with the understanding that we're going to do these problems with some basic level of, well, how would we do any other graph? Well, every single graph that we'd ever do in terms of graphing, if we don't know what it looks like, we're always going to build ourselves a table of values, so x and y. Keep in mind that nowhere in here does it define x to be anything other than what every option can be. So we can start off at negative numbers and work our way up to positive numbers. I'm going to start with the two most prominent values you're always going to try and identify. And those values are plugging in 0 specifically for the exponent, and plugging in 1 specifically for the exponent. And when I say that, what I mean is even in these more complicated examples up here, you want the exponent to end up being 0. So what x value would I have to plug in to get back 0 for the exponent? And the same goes for what x value would I have to plug in to get back 1 for the exponent. Those are the values that I really want to play with for this example. So when I plug in 0, I'm going to get back a value of 1 because 3 to the power of 0 is 1. Now, if you don't trust that, let's go through the pattern. If I plug in 1, I know 3 to the 1 is 3. If I plug in 2, 3 to the power of 2 is 9. If I plug in 3, 3 to the power of 3 is 27. Now, these rules all make sense. Now, again, if you don't trust the rule that 3 to the power of 0 is 1, well, then just follow the pattern. I lose 1 value on this side every single time, and on this side I'm dividing this value by 3. So 27 divided by 3 to get to that one, then divided by 3 to get to that one, then divided by 3, it should get me back to 1. So sure enough, if for this function I plug in 0, I should get back 1. This actually holds true for any value. No matter what exponent I have, no matter what base I have, as long as it's an exponential function, I plug in 0, anything to the power of 0 should still give me back 1. And again, it's because of this rule of patterns that makes sense. So after that, basically what happens when I plug in negative values? Well, that should hopefully reinforce the understanding of how those negative values come to be in terms of, in the exponent, I get back a fraction, because I'm simply going to follow that pattern of division, dividing by 3. So in this case, if I divide the 1 by 3, I'm going to get 1/3. And sure enough, that's where it should make sense that if I have f of negative 1 equaling to 3 to the negative 1, the negative exponent by definition always ends up being that fraction. And again, that reinforces that algebraic rule that we should feel comfortable understanding and recalling. So with all that being said, we can go ahead and sketch this graph. Again, the most important points are this one here, 0, 1, this one here, 1, 3, and then there's one other important piece of information, and that's the asymptote that we're going to draw. An asymptote, remember, if you don't recall, is a guiding line to the function. It is an imaginary line that doesn't actually exist, but it is a line that the graph will never cross. For exponential functions that aren't shifted in any way, the asymptote will land specifically on the x-axis. So you're going to have 3 important pieces of information. The asymptote, in this case, it's going to be y equals 0. You're going to have your y-intercept point. Again, it might not actually be a y-intercept point, but it's where we're going to look for the inside value of the exponent being 0. So if I plug in 0, I get back 1, so I've got that point. And then the last point is that extra individual point, so the 1, 3, where the exponent gives me back 1. And that I'm not going to label as anything. But those are the 3 important pieces of information. If I can get those 3 important pieces of information, everything about this graph should fall into place logically. So if I go to graph these, I get 0, 1, which is approximately right there, and then I get 1, 3, 1, 2, 3, so right about there. And again, it's supposed to go away from exponentially the asymptote in one direction, and it's supposed to approach the asymptote in the other. And again, the reason why this should make sense at all is because as I keep plugging in negative numbers for x, you'll notice that this fraction here is just simply going to be divided by 3 again and again and again. It'll never actually approach, it'll never actually reach 0 or reach a negative number, but it will get closer and closer to that value of 0. So this is the basic graph of f of x equal 3 to the x, and every single graph will look something like this, where it has a horizontal asymptote, again a horizontal asymptote, and it has those 2 important pieces of information, one going away from the asymptote and one going towards it, in which case, again, we're just going to go ahead and draw that. Now keep in mind, in your graphing calculator, it might end up showing it looking a little bit steeper here, so it looks like it actually tapers off, but this doesn't taper off. It just continues on forever, continuously increasing, getting larger and larger, while this one here is tapering off, approaching that asymptote, flattening out, but never actually reaching that value. That is, again, the basic information of an exponential function. In the next video, we'll cover more examples of how modifying this equation will change what this graph looks like and how to easily deal with transformations of these functions.